we better discuss some of the topics that we missed last time. In a metal semiconductor junction, the band diagram is going to look like this. This is Fermi energy, and then you're going to have a band bending like this, and then we call this whole area as a depletion region. Okay. And here, if we set the vacuum level like E naught, and then this E naught is going to be bent accordingly to the conduction band of a semiconductor, like this. And this energy is going to be called the work function. And basically in a metal, you have electrons to the top of the Fermi energies, like this. And here, this is the barrier energy barrier that we discussed the last time. And this distance is the phi I, the built-in potential. So I think okay, this is a built-in potential. And the energy difference from here to here is a chi, affinity. Okay? And so at equilibrium, we don't expect any electrons, free carriers, move to from semiconductor to the metal, or metal to semiconductor. There should be no current at equilibrium. And to find it out, if you want to see the flux of electrons, if you like, from semiconductor to metal, for this flux, the electrons has to overcome, phi I should be overcome. Because most energetic electrons in a semiconductor is the electrons at the conduction band that is free to move, and the barrier, the built-in potential, has to be overcome to move for the electrons to metals, right? And we know the number of electrons in conduction band. That is going to be N is equal to NC e to the minus phi F over phi T. Okay, that's a Boltzmann, right? And the phi I is the Fermi energy, and the phi T is the thermal energy, which is Q over KT. All right? So the flux of electrons from the semiconductor to metal is going to be n times number of electrons available n e to the phi I over phi t, which is a Boltzmann statistics, which overcomes the activation energy phi I. So this is going to be the flux from semiconductor to metal, and we know this n is corresponding to nc e to the minus phi f. Okay, so if you multiply that with Boltzmann statistics, you end up with some equation which is going to be here, and this is nc e to the phi b over phi t. This sum is nothing but the barrier height. Okay, and for the flux metal to semiconductor now is going to be nc e to the phi b over phi t. So F flux of electrons from semiconductor metal is exactly the same to the electrons metal to semiconductor. That is equilibrium. Now what happens if you apply the bias? Apply the voltage phi A, okay? Then the flux from semiconductor to metal now, and subtract the semiconductor to metal at equilibrium, is now going to be nc e to the minus phi b plus phi a over phi t minus nc e to the minus phi b over phi t, and that is going to be nc e to the minus phi b over phi t and e to the minus phi a over phi t minus 1. Okay, and this is going to be called I naught. And that is a constant value, which is not changing on the applied voltages. Okay, phi b is the barrier height. Once you form the junction between metal and semiconductor, phi b is fixed. And nc, we know, is the effective density of states in the conduction band of the semiconductor. So this is the fixed number, this is the fixed number, so that we call this I naught. Okay, and this is the correction part according to the applied voltage phi A, right? And the next topic that we missed last time is probably, I just briefly mentioned about the tunneling to get an ohmic contact between metal and semiconductor, right? So let me just say something more on this ohmic contact. That this ohmic contact between metal and semiconductor is very important in semiconductor devices. So for ohmic contact, if the semiconductor is the n-type, then the work function of metal should be less than the semiconductor work function. And the semiconductor work function is nothing but a Fermi energy plus the affinity. According to the band diagram that I just erased it. But, so for p-type ohmic contact, we should have the work function of metal should be greater than the semiconductor work function. Now let me give you the typical example. If we use the aluminum as a metal, this is a typical case, right? The aluminum work function, well, aluminum metal work function is a 4.2, okay? And chi, the silicon affinity is a material constant, which is 4.05. This affinity is a material constant. Material constant. Okay, it's not dependent on the doping or whatsoever. Okay, so for ohmic contact, okay, for n-type case, the 4.2 should be less than 4.05 plus the ferroenergies of the semiconductor. For p-type, okay, this 4.2 should be larger than 4.05 plus ferroenergies. Simple, all right? And typically, for the semiconductors, this ferroenergy is about 0.5, okay? Typically, the ferroenergy is about 0.5 volts. So n-type case, it's blocking always. It's not ohmic contact. You cannot obtain ohmic contact if you use aluminum as a metal on the n-type silicon, because of this. Now, in a blocking contact, it's going to look like this, and we mentioned that this is the built-in potential, okay, and this is the conduction band bending, and this band bending is related to the built-in potential, and this built-in potential is very much dependent on doping of the silicon, of course. And the XD here, the XD is the depletion length, okay? The XD is typically, it can be calculated to find these numbers, Q and D, and phi I. So you can see if you dope the semiconductor heavily, then this XD, the depletion region, can be shallow. The number of the depletion layer length is very short, okay? So if you heavily dope n-type, like source and drains in MOS transistors, then tunneling is possible. Due to very small number of this XDs. So actually what's going to happen is that the electron is going to tunnel this shallow depletion layers so that it becomes ohmic. This ohmic contact is very important because if you cannot guarantee the ohmic contact, then what's going to happen is that if you apply the voltages, certain voltages as an input, that voltage is not going to be transferred to the transistors, so that because of the high resistance due to the blocking contact, if you have a blocking contact. So that device is not going to work. So you have to guarantee the ohmic contact all the time in the device. And this is the things that we are doing in the industries. You heavily dope the N-type region in the CMOS so that tunneling happens and we can get the ohmic contact in the N-type. P-type, there's no problem. P-type always is ohmic contact. Okay? And the next topic that we missed the last time maybe is a breakdown phenomenon. Now, XD can be expressed as a Q and D in the metal semiconductor junction. And now if you apply the voltages to it, this built-in potential is going to be modulated by the applied voltages, phi A. I'm sorry. Only the unit is different. Okay. So if phi A can be increased, then this XD is going to decrease, and Emax, which is Q and D over K E naught XD, is going to increase. Okay, I should express in this fashion so that the electric field inside the metal semiconductor junction is going to increase accordingly with the applied voltages. Then the breakdown happens, and this breakdown can be, two phenomena is related to this breakdown phenomenon. One is the avalanche breakdown, and the Jenner breakdown. Avalanche breakdown is generation of electrons and holes, like avalanche in a mountain. When a silicon atom is going to be hit with high energy electrons, okay, then this silicon is going to generate electrons in hole pairs, and this is going to be called the breakdown of covalent bonding. Covalent bonding of silicon. All right? That is the avalanche breakdown, and the general breakdown is the breakdown generation of electrons and holes at the space charge regions. In the space charge regions, only ions are here, and if it is a metal semiconductor junction, then in the semiconductor part, only the depletion region occurs in the semiconductor part, and here at the depletion region, only ions is exist in only ions here, and then at this space charge region, the silicon can generate the electrons and holes. So generation of electron and hole pair at the space charge region. That's going to be called the general breakdown. And last time we have discussed about the PN diode, and today we're going to discuss about the PN diode in details. Okay. Now we have at equilibrium, we're going to have band bending like this in a PN diode, and then you can draw the intrinsic level EI and the conduction band and the valence band, something like this, right? And then we can see the gap here, ferrome energy and the intrinsic level, that is going to be used. This energy is going to be used for to get the numbers of free carriers and energy states and so forth. Okay. Now the built-in potential and the ferrome energies, a built-in potential with respect to the intrinsic level, it can be written as Vt ln nd over ni, okay? And phi I, which is a built-in potential, and that is Vt over ln nd na over ni square in this PN junctions. Now we have contributions from the N side and P side, both in these PN junctions. In a metal semiconductor junctions, the metal, it has it does not have any contribution to the built-in potentials. Okay, but in a PN junctions we have a contribution from both sides, and we're going to assume the neutral and the depletions. This has been discussed the last time, and the transitions. Regions, and we have discussed about the length of this transitions, LD, as Q Vt over gamma Nd minus Na, something like this, right? Where the gamma is Q over K E naught. And that is typically about the 300 angstroms that we have discussed the last time. And in the step junctions, if we assume that step junctions, which means the transition region is 0, okay, that is the step junction. D square Okay, that is a charge according to the Poisson's equation, and charge neutrality NA XP is going to be ND XN, and W is the total length XP plus XN, and electric field, it's going to be first integration of these charges, and that is straight line according to the x. And the phi n is going to gamma. You make an integral of this electric field from xn to x, and then you end up with gamma nd over 2xn squared. Okay, and then phi I, built-in potential, is going to be max times W. That's simple. So if we draw in this step junctions the charges, then you have some values, something like this, and then if you plot the electric field according to this depletions, then it's going to be something like this, a straight line, and this is going to be E max. And if you plot the phi, okay, then you have a changing in phi, like this is a phi n, and this is going to be phi p. Something like this. And the W, the depletion width on both sides can be written as NA minus ND minus. This NA minus is 1 over NA. And gamma, again, Q over K, so that. And we discussed about the junction capacitance. Which is Q over A, and then Q ND XN Q NA XP. Okay, and the capacitance by definition is going to be modulation of these charges with respect to the applied voltages, and then that can be expressed simply by dx dv, change in the depletion length with respect to the applied voltages. So that is the only variable with respect to the applied voltages. The other terms are just fixed. So the capacitance can be written simply just like this. And we know Xn and Xp is going to be W. And then now let's say this is XD. And since ndxn plus naxp equal, for the charge in neutrality, xn xd minus xp now it is xd minus 1 over 1 plus nd over na, and then 2 over gamma and a and d phi I minus VA over one plus ND over NA. Okay. Now TN TVA is going to be 1 over ND. Let me make it consistent like ND. There is 1 over ND. And then root 1 over 2 gamma times 1 over NA bar and D bar phi I minus VA, built-in potential. Then capacitance is QND over dVA over dXN, okay? So that it's going to be Q over 1 over 2 gamma and 1 NA bar plus ND bar phi I minus VA. That is the capacitance of this PN junction. And physically, you can see that the depletion region is working as a space between two metals in a capacitor, normal capacitor. Now let's see, this looks complicated, but as in most cases, let's say one of the doping level is greater than the other, so that we can simplify this like Q over N D over 2 gamma phi I minus VA, something like this. Okay, what does this mean? It means that if you the lightly doped region controls the electrical properties of the junctions, like a capacitance. Capacitance is depending on the lightly doped dopant density, right? Instead of a heavily doped regions. And of course, if you get these equations, ND over 2 gamma phi I minus VA, something like this. So if you make a plot, 1 over C squared and VA, then you are going to have a straight line, and this slope is corresponding to 1 over ND. You can directly get the numbers for this, and then of course this intercept is related to the built-in potential. So if you measure the capacitance of the PN junctions, then you can get this values. Generally, capacitance of the junctions can be written as Cj phi 1 minus Va over phi I, and with minus m. This is the general expressions. And Cj phi is Q silicon epsilon and Nd Na over 2 phi I built-in potential Nd plus Na here, and then plus M. And phi I, that is the built-in potential, which is going to be Nd Na over Ni square. Now for step junctions that we have discussed right now, this M is going to be 0.5. If it is not a step junctions, we should find M proper for that junctions. Okay? Now, let me just discuss about the CV characteristic. CV characteristic. And let's define some of the designations, like e to the phi I minus Va over Vt, and the Pp. We have discussed about this last time. Pn e to the phi I minus Va over Vt. Okay? And n naught is np naught e to the phi I over Vt, and n pp naught pp naught is the equilibrium value. It's going to be e to the phi I over Vt. All right? And phi n is Vt ln Nd over Ni, and phi I is Vt ln Nd Na over Ni square. Now, if you just think about the electrons across this depletion regions, where this is the actual junction is made, and then in the depletion region we just have the ions, no free carriers, so we just only have ions. And let's suppose we have electron concentration, equilibrium electron concentration in n side, like this. And on the p side, this electron concentration on the p side is going to be somewhere around here, because it is a minor carrier in the p-type region, and this is the majority carrier for the electrons in the n side. So the concentration is somehow going to change something like this. And this change in concentration contributes to build the built-in potentials in this case. Now, if we look into the low-level injections, we are not going to discuss about the high-level injections. Low-level injections by definition, this low-level injection means N is almost the same to the N naught, which means majority carrier is not changing upon application of voltage VA. Right? That is the low-level injection. Okay. Then N is going to be NP e to the phi I minus VA over VT. Right? And this is going to be NP naught e to the phi I over VT. So NP is equal to NP naught e to the VA over VT. What does that mean? It means in this drawing, if you have, let's say, p-type, p side here, and then this is the n side, n-type, and we have a depletion like this, we have an equilibrium value for p naught, and equilibrium value for the NP naught. This is a minority carrier, and then this is a majority carrier here. And here, the N naught and P N naught, something like this. Okay, we have a minority carrier concentration and majority carrier concentration in each side before application of the voltages. And by applying voltages VA, now this majority carrier is not going to change much. That is a low-level injections. But this minority carrier is going to change with this low-level injections. And then this one is going to go down and set up a new value here, which is N sub P, new minority carrier. And that is this values and P naught times applied voltages is going to increase or decrease exponentially with the applied voltages. That's what this low-level injection is about. Okay, it is going to change like this. And what about this minority carrier? It's going to set a new values Pn, and that is Pn naught times exponential term like this. So the low-level injection says if you apply the voltages in a p-n junctions, your majority carriers are not going to change, but the minority carrier is going to change exponentially with the applied voltages. Okay, that is a key point. Then what's going to happen? We call this injected carriers. Okay, I just draw it as a decreasing, but in normal case, you just increase the minority carriers, which has been injected from the majority carrier on the other opposite side and the junctions. So at the depletion interface front, you have new values of Pn, and this minority carrier Pn originally has equilibrium values of Pn naught, and we have just seen that this Pn is increased according to this equation here, exponentially increased. Okay. In other words, this is going to be Pn naught e to the phi I over phi t, or Va over Vt, Va over Vt, thermal voltage. Now, somehow this injected minority carrier is going to decrease to get the equilibrium values far away from the junctions, right? So we call this is the injected charges or injected electrons to the opposite side. All right? Then we can apply the Fick's law. We have a concentration gradient. Then we should have a flux. Okay, that is the Fick's law. So the IP, the current, that is a flux QA, that is the area of the junctions, and the diffusion Fick's first law. That is the Fick's first law, right? And we know the continuity semiconductor equations. dP over d round x square over round square Pn minus Pn naught over tau. Right? So at steady state, this changing and the concentration should be 0, and with proper boundary conditions, we can see that delta P is going to be Pn naught e to the Va over Vt minus 1 times e to the x minus xn over Lp, where the Lp is the diffusion length. All right? And dPn over dx now is going to be delta P over Lp. And if you put that thing on the first equation there, the current that you can get now is going to be related to the diffusion coefficient and the characteristic length in this fashion, delta P. Now we have a contribution of both sides, and that is current, hole current, and an electron current, X equal XP. That has different directions that flows, the flux flows, but the sign, the charges is opposite, so that the total current should be added together. And I total now is going to be QA dP P N naught over LP plus dN and P naught over Ln e to the VA over VT minus 1. And this is again is going to be called I naught in this case. And you can compare the current in the metal semiconductor junctions. And then this is I naught e to the VA over VT minus 1. That is the current that you can get out of this PN junctions. And if you look into the I naught, which is here, you can see that is dP over ND LP plus dN over, let's make it consistent, and large capital letter, ND or NA or Ln. So you can see here lightly doped semiconductor will control I naught value. Okay. And charge Qn is going to be Q A N P naught e to the VA over VT minus 1 Ln and QP QA Pn naught e to the VA over VT minus 1 LP. Now, if P plus N minus junctions, which means the P type is heavily doped and N side is lightly doped, then the charges here is going to be equal to the charges from the P side, and the characteristic time tau is defined such that the current is going to be the charge over the characteristic time. Then this tau is going to be calculated, derived like this: tau p dp over dp, so that is a tau p. Here LP, the diffusion length is tau p dp. Okay. So that is pretty much about the p-n junctions, and we're not going to go for the charge models, injection models in this p-n junction. We're going to discuss about the charge controls in the p-n junctions in bipolar transistors later. So up to here, it's going to cover the topics related to the p-n junctions, and the next section is the application of p-n junctions, and note you can see the many applications. I think it's about the 7 applications has been introduced in a context, and we are not going to discuss about those applications, but I want you guys to look into the solar cells, especially solar cell parts as an application, and the heterojunctions, and in application topics. I want you guys to look into those 2 chapters carefully, okay? Even though we are not going to discuss about those 2 topics in this class. Next class, next week on Monday, we are going to talk about the MOS transistors, operation principles of MOS transistors. Okay, have any questions? And have a nice weekend, and I'll see you guys on Monday next week.